Good morning, everyone. My name is Federico Tuozzo. I am a PhD student in structural geotechnical engineering and seismic risk at the University of Naples, Federico II in Italy. This year, I had the opportunity to spend a research visiting period at the University of Miami under the supervision of Professor Antonio Nanni. It's a great honor for me to participate for the first time at this convention. I would like to thank you for the opportunity. The question we are addressing today is GFRP limited to no seismic zone? To answer this, we will analyze the property of glass fiber-reinforced polymerous materials, GFRP. On one hand, it offers advantages such as high strength, corrosion resistance, lightweight, and durability. On the other hand, it has limitations including brittle behavior, lower stiffness, and lower workability, which impair its use in seismic zone, especially for the structure designed for energy dissipation as required by the Lastis Code. To address this challenge, I will present the work carried out by my research group and proposed an innovative hybrid section. After the pre-design phase, we focused on the beam and was designed with three different approaches, one of which is hybrid, and the designed beam was analyzed through finite element and analytical methods, as we will discuss shortly. The case study involves a reinforced concrete moment-resisting frame for residential building, regular in both plane and elevation, designed according to the current code for high seismic hazard site, such as seismic design category D, for example, according to ESC 7. And after the pre-design phase, we focused on the beam highlighted in the figure, and the choice of this beam reflect its greater exposure to environmental element with respect to the beam in the inner part of the building and its greater demanding load with respect to the beam on the other floor. The beam highlighted in the figure was designed with three different approaches. The first, a reinforced concrete section with traditional steel rebar according ACI 318. The same cross-section with the same bending capacity, but with GFRP reinforcement according ACI 414, and the last, the innovative hybrid section with the same cross-section and the same bending capacity that maximize the property of material involved in the section. The GFRP used as stirrups and longitudinal reinforcement placed in the other part of the section reduce the cover with respect to traditional steel section due its resistance corrosion, while the steel reinforcement in the inner part of the section doubled the cover with respect to traditional steel section and improved durability and ductility of the section. The design approach was conducted according to the current code with some adjustment to consider the combination of these two materials involved in the section. And this approach aims to improve the sustainability and durability of reinforced concrete construction. The design approach followed the current code, in particular ACI 414 for the element reinforced only with the GFRP, and ACI 318 for the element reinforced only with the steel, with some necessary choice and modification to consider this innovative hybrid section. In particular, regarding the strength reduction factor for tension-controlled section, the current code proposed 0.55 for the element reinforced only with the GFRP and 0.9 for the element reinforced only with the steel. The lower value of GFRP reflects its brittleness and with a significantly reduced of capacity during the design phase. However, in the hybrid section, the addition of the steel compensates the lack of GFRP ductility. For this reason, we propose to adopt a value according to ACI 318 for the element reinforced only with the steel. Adopting the steel strength reduction factor for tension-controlled section implies referring the strain minimum reinforcement area and balancement reinforcement ratio requirement similar to the steel. For brevity, I will not go into the details about this choice, but regarding the shear strength, we proposed to consider only the contribution of the concrete and the GFRP stirrups. This is a safeguard approach, and there are no established models currently in the literature for evaluating the capacity of this innovative hybrid system with stirrup arranged into two different layers and made from two different materials. About the concrete contribution to the shear strength, the current code proposed formulas differ to the reduction factor associated of GFRP reinforcement, caused by its lower elastic modulus, which results in greater deformation and cracking for the element reinforced only with the GFRP, and this crack impair the shear strength of element reinforced only with the GFRP. However, in the hybrid section, the addition of the steel in the inner part of the section improved the stiffness of the element, leading a response similar to the element reinforced only with the steel. For this reason, we proposed to adopt a formula according to ACI 318 for the element reinforced only with the steel. The proposed approach summarized here and will be validated with further numerical simulation and experimental test, and more details about this approach are reviewable in the paper currently under review. The proposed approach lead to design 3 different beams with the same cross-section and the same bending capacity, compliant with the respectivity code requirement. In particular, for the steel reinforcement, according to ACI 318, including the seismic requirement, and for the GFRP reinforcement, according to ACI 414. The designed beam was verification in seismic zone through the Eurocode 8. American code mainly prescribe check for seismic zone only in terms of dimension and reinforcement quantities, while Eurocode 8 include a local ductility check in terms of the curvature. The demand was evaluating assuming the equivalence between the behavior factor from Eurocode 8 and response modification coefficient and importance factor from ASC 7. The demand depending to the characteristic of the structure and the seismic site, while the capacity was evaluated according to Eurocode 8 as a ratio to ultimate curvature at the yielding, and in this case study was evaluated through analytical and finite element methods. In particular, for the section analysis, the material property considered are shown in this figure. And here we present the section analysis of hybrid section, evaluated by determining the equilibrium curvature at different limit state, yielding of the steel, elastic limit strain of the concrete and both confined and unconfined the ultimate strain of the concrete. Obviously, this analysis section was conducted for all beam designed, and the results are shown in terms of moment curvature curves. These curves show that the hybrid section has a similar performance to the steel section in terms of capacity and in terms of ultimate curvature. The hybrid section has a low stiffness with respect to the steel section and strangely low ultimate curvature with respect to the steel section. Due its lower elastic modulus of GFRP rebars and the ultimate strain deformation with respect to the steel section. But as shown in the table, the hybrid section and the steel section meets the requirement in terms of local ductility for high seismic hazard zone according to the Eurocode 8 in terms of ductility. While, as I suspected, the section reinforced only with the GFRP show a limited ductility and inadequacy for seismic zone according to the Eurocode requirement. The section analysis was validated through finite element model using OpenSys software, adopting a fiber approach to consider the different material involved in the section, confined and unconfined concrete, steel, and GFRP. The property of material implemented in the software are shown in the figure, and the analysis was conducted through incremental static analysis in displacement control, and the results are shown in terms of moment curvature curves. The results confirm the results obtained through the section analysis, in particular in terms of capacity of ductility. The value differed due to less 10% with respect to the results of section analysis. And both methods confirm the adequacy of hybrid section for seismic zone according to the requirement of Eurocode 8. The difference between the two models in terms of the strength due the different behavior and property of material implemented in the software, in particular differ to design value and average value of property of material. Obviously, with the same property, the two models match. In the light of these results, we can affirm that the use of GFRP is not limited to non-seismic zone. Both methods showed adequacy of hybrid section for seismic zone according to the requirement of Eurocode 8. The hybrid section show performance similar to the steel section in terms of strength and ductility, and improve significantly the ductility with respect to the beam reinforced only with the GFRP. Experimental test and further analytical simulation are the next step. I conclude by thanking you for the attention.